Hello, and welcome to this Let's Talk Meshing webcast. We often encounter users with questions about how to distinguish a mesh with good quality characteristics from meshes that are considered poor. Typically, the idea that a mesh consists entirely of positive cell volumes is a minimum requirement ensuring that the mesh is likely to run with a robust general flow solver. However, how well the resulting flow solution accurately represents the physical system being modeled, as well as how efficiently the flow solver converges to the solution, are all influenced by characteristics of any given mesh. Furthermore, one mesh configuration may be more suitable for accurately representing a given objective function like the lift-to-drag ratio, while another configuration would be used to reliably predict a different objective function, such as pressure drag. While a priori mesh quality assessments can be useful, particularly with flow solutions involving simple models where experienced practitioners can anticipate interesting flow features, oftentimes this can be difficult to accomplish when more complex geometries and flow physics are used in simulations. One approach around this issue is by changing the mesh in response to the developing flow solution. This is known as mesh adaptation. Having worked throughout industry for several years, mesh adaptation isn't new. However, my experience has shown that mesh adaptation is typically underutilized in practice, whereby very few specialists throughout academia and industry regularly incorporate it into their simulations. Perhaps the difficulty in obtaining a quantitative estimate of discretization error, which would remind practitioners of the imperfect nature of CFD and highlight the magnitude of errors between a given CFD solution and the analytical or physical system being modeled, may be responsible. Probably, more often than not, schedules don't allow enough time for practitioners to perform a rigorous estimation of discretization error for each solution they generate. However, error estimation and adaptive methods are key enablers for improved CFD predictions. Metric-based mesh adaptation typically involves two steps. The first step is to construct a metric that describes the desired size and anisotropy of the adapted grid elements. The second step is to produce an adaptive grid that is based on this metric. Within this framework are two alternative approaches: feature-based adaptation and adjoint-based adaptation. Feature-based or local error-based adaptation constructs the metric based on properties of the flow solution. Adjoint-based or output-based adaptation constructs the metric from the flow and adjoint solutions to reduce estimated errors in a specific engineering output function. The mesh adaptation mechanics themselves also vary widely from simple point insertion to more general implementations that incorporate node movement, collapsing elements, and swapping elements to iteratively drive mesh generation to satisfy an anisotropic metric. To demonstrate how this process works, I'm going to walk through the process of making an initial coarse mesh in pointwise to solve for the flow around an Onera M6 wing using the adjoint-based adaptation mechanics included in NASA Langley's Fun3D flow solver. By starting with a coarse grid and scheduling successive limits on the grid complexity, the execution time on initial grids can be reduced. The control pointwise offers its users and its ability to resolve highly curved surfaces using anisotropic cells are extremely valuable in creating a coarse mesh while still resolving the analytical features of this geometry. The Onera M6 wing was designed in 1972 by the Onera Aerodynamics Department as an experimental geometry for studying three-dimensional high Reynolds number flows. This widely known wing geometry serves as a reference model for validating new numerical methods and CFD codes due to the availability of empirical data and intriguing flow features which include a strong adverse pressure gradient over the wing's upper surface due to shock formation in transonic flows. Lastly, we were interested in whether the type of near-wall elements had any influence on convergence and accuracy of this process. So we repeated the mesh adaptation procedure twice. To investigate this, we exported two separate grids from pointwise. The first grid was created using an all-tetrahedra mesh, and the second grid utilizes pointwise T-Rex cell combination feature to combine the anisotropic tetrahedra of the first grid into prisms without modifying any of the isotropic tetrahedra in the far field. To begin, let's open Pointwise and from the File menu, select Import Database. From the Open Save dialog window, I can navigate my file system and select the Onera M6 geometry file, and I'll accept the default options in the Import Database panel by clicking OK. First, I want to get a sense of the model's size. I do this by selecting Properties from the File menu. The Properties panel opens, and in the table at the top, I can see the total length of the model. For this model, I note that the units here for the Onera M6 wing are likely in meters, since the root chord for this wing is 0.8059 meters. I prefer to work in inches, so I will want to scale my model by a factor of 39.37, which gives me a model size here of 47.66 inches. To scale the model, I can select the model from the List panel or Display window, select Transform Scale from the Edit menu, and enter an anchor point and scaling factors using the corresponding entry fields. The Display window will update with a preview of the scaled geometry outlined in yellow. To accept these changes, I simply click OK. I also have a preferred orientation when meshing, so I'm going to mirror the wing about the y-axis by again selecting the model and choosing the Transform Mirror option from the Edit menu. To mirror the geometry about the y-axis, I'll select the corresponding radio button and then select OK to accept this transformation. If I select the model and navigate to the Assemble Models panel via the Assemble Models option under the Create menu, then I can see that my model consists of 6 lamina boundaries. Lamina boundaries are free edges. I should have only 3 lamina boundaries from the edges that appear along the model's symmetry. Thus, this model has a missing surface, or hole, somewhere which happens to be at the trailing edge of the wing near the tip. To make this hole more visible, I'll toggle the rendering of surfaces from a wireframe display to shaded surfaces using the pull-down menu available in the toolbar. The missing surface appears adjacent to the finite trailing edge and perpendicular to the tip or wing cap surfaces as shown. I can quickly resolve this issue and create a watertight geometry model by creating a Kunz patch and associating this patch with the model. To do so, first, I want to select only the database boundaries selection mask from the toolbar. Then I can select the 3 bounding edges using an inclusive box selection in the display window by holding the left mouse button and Shift modifier key on the keyboard and dragging a box around the edges. Once I have the edges selected, I can select Kunz Patch from the Create menu. This brings forward the Kunz Patch panel, and simply clicking the Generate Surfaces button with the default bit tolerance will create a rational B-spline surface from the selected edges. The display window will provide a preview of this surface outlined in yellow. To save this surface, click OK. You should notice that a new B-spline surface has appeared in the List panel. Selecting this surface in the List panel and changing the display property from wireframe to shaded makes it more readily visible in the display window. Now, I need to associate this newly created surface with the model in order to make my model watertight. I can do this by selecting the model and B-spline surface from either the List panel or display window, and then click the Assemble Models toolbar shortcut. The Messages window prints out the result of this operation, indicating that 2 models and/or surfaces were combined into a single model and there were no unused surfaces. The surface type has also been updated from a B-spline surface in the List panel to a quilt. In Pointwise's terminology, a quilt is the engineering representation of a surface in your model. You can organize these quilts into logical groups that you may want to use in resolving specific features of your geometry and/or isolate for use in force and moment integration calculations. Here you can see that I've already organized this model into a few groups, like the upper surface, lower surface, trailing edge, and so forth. Each of these quilts are actually defined by one or more B-spline surfaces included in the original geometry definition, and our model is simply a collection of these B-spline surfaces. If I now select the model again and go back into the Assemble Models panel, I can see that I now only have 3 lamina boundaries, which correspond to the known edges at the model's symmetry plane, thus confirming that my model is watertight. One last thing I'll do before I start meshing is color my model by the quilts that compose it. To do this, I'll first toggle all of my selection mask off using the toolbar shortcut and navigate to the Mask panel via the Mask option under the Select menu. Here, I'll toggle off all of my database selection masks except quilts and click OK. This allows me to select only the quilts in my model, and I can select all of them at once by left-clicking and dragging a selection box around my model. With all of my quilts selected, then I can give each one a unique color by clicking the Rainbow Toolbar shortcut item. The display window will update, and I can more easily visualize how the quilts of my model are organized. The wing cap on the tip of the wing is composed of 2 quilts, and I can represent this more simply with a single quilt, so I'll go ahead and combine those 2 quilts into one. Select both quilts using either the List panel or display window, and then click on the Assemble Quilts toolbar shortcut. The Messages window confirms that both quilts were combined into a single quilt, and the display window updates indicating that the wing cap consists of a single quilt. This process of assembling surfaces into a single model and then combining and organizing the quilts of that model is what we refer to when we talk about solid modeling. It is a useful technique to help expedite creation of high-quality surface meshes, as I'll demonstrate next. To begin meshing, I'm going to first set a few defaults by clicking over to the Defaults panel. I have a preference for the Advancing Front Meshing algorithm, so I'm going to switch to that from the Delaunay algorithm, which is set by default. The Advancing Front algorithm generally produces a domain which is more uniform in appearance, but both algorithms should produce grids of similar quality. I'm also going to increase the boundary decay setting from 0.5 to 0.85, which should increase how far into the domain's interior the boundary cell size affects the interior cell size. Lastly, I'm going to set the average grid spacing for newly created connectors and domains. I'm going to use a relatively large value here, as again, I want my mesh to be coarse while still being able to resolve the surface of my Onera M6 wing model adequately. With my average grid spacing set, I'll switch pointwise into the unstructured mode for creating unstructured grids, select my model, and from the Create menu, select the On Database Entities option. Here, I want to ensure that the Domains radio button is selected, and then I'll specify a connector join angle of 30 degrees. This option is useful for automatically joining newly created connectors where there are no features in the database geometry to represent by breaks in the topology. Click OK, and database-constrained unstructured domains are created. By toggling off the display of database entities and changing the display mode of domains from wireframe to hidden line makes visualizing the newly created unstructured domains in the display window that much easier. The first thing I notice about the surface mesh is that I don't have adequate grid resolution at the leading edge, so I'm going to use Pointwise's 2D T-Rex feature to resolve that curvature on both leading and trailing edges with anisotropic triangles. To do so, I'll edit the beginning and ending spacings for each of my connectors to something more reasonable like 0.1 inches. I can accomplish this quickly by toggling on only the spacings constraint mask from the toolbar, drawing a selection box around all of my connectors, and then using the spacing entry field in the toolbar to change all of the spacings to 0.1. Next, I'll select all of the connectors in order to change the grid distributions using the Distribute panel, which can be accessed from the Grid menu. On the Functions tab, I'll change the distribution function for these selected connectors from the default hyperbolic tangent function to a growth distribution using the corresponding radio button under the function frame. Next, I'll expand the growth distribution parameters frame by clicking the checkbox next to it and set the parameters which will control the growth distribution using the initial spacing I just set on the connectors, a growth rate, and the number of layers to generate at each end of the connector. A typical growth rate to use is something greater than 1 and less than or equal to 1.2. To determine an appropriate number of layers to use, we usually target an aspect ratio for the anisotropic cells that we want to generate. A good range for this is typically something between 10 and 20. Here, I'll select 20, and using both the target aspect ratio and desired growth rate, I can determine about how many layers I should create using this formula. In this case, I want about 16 layers. With this initial spacing, growth rate, and growth distribution, my initial dimensions for these connectors is a little too coarse. To correct this, I can click over to the Dimension tab, select a connector in the display window, and have pointwise set the optimal dimension for the selected connector in order to have a smooth distribution of points along each connector. I'll click OK to save these changes and exit the Distribute panel. Now, I can use 2D T-Rex to generate anisotropic triangles with an aspect ratio of 20 along the leading and trailing edges. I'll select the upper and lower surface domains, and then from the Grid menu, select T-Rex. I'll click over to the Boundary Conditions tab and set up the requisite boundary conditions before proceeding. Here, I'll create a couple of boundary conditions for the wing leading edge and trailing edge. Set those to wall BC with an initial spacing of 0.1, and then create a boundary condition for the root and tip connectors where the type should be set to a match BC. Then, I just need to assign each connector to its corresponding boundary condition by first selecting them in the display window and then clicking the checkbox next to the corresponding BC. Once my boundary conditions are set, then I can navigate back to the T-Rex tab, set the growth rate and number of layers using the appropriate entry fields, and then click on the Solve tab and run T-Rex. This looks pretty good, so I'll click OK to save these changes and exit the Solve panel. My surface mesh is about done. Before I proceed with creating the far field and symmetry domains, I want to examine the surface mesh quality. Selecting all of the domains and choosing Area Ratio under the Examine menu brings up the Examine panel with an area ratio function selected. It shows that my max area ratio is about 8. But that maximum occurs in only 2 neighboring cells where the trailing edge and wing cap intersect. I could fix this by selecting a grid spacing more on the order of the trailing edge height, but for this coarse mesh it should be okay. The rest of the mesh is under an area ratio of 4, which is a good guideline. Alright, on to creating the far field and symmetry domains. First, I'll create a half circle curve by selecting the Draw Circle option under the Create menu. Then I'll toggle the entity type to that of a database entity, select the Point, Center, and Angle radio button under the Circle Segment Options frame, and then proceed to provide a point on the circle, a center point, and a 180-degree angle for a half circle segment. I've determined the center point by using half of the extent of my model, which is shown under the same Properties panel we used when initially importing the database geometry. The point on the circle is ultimately the radius of this circle, which is about 10 root chord lengths. Once those 3 parameters have been provided, the display window shows a preview of the segment, and if appropriate, I can flip its direction. To save that segment and exit this panel, I'll click OK. Now, using this curve, I'll create a surface of revolution using Pointwise's built-in tools. Under the Create menu is a Revolve option dedicated for just this purpose. After selecting this curve and opening the Revolve panel, I'll select the Point and Direction radio button under the Axis selection frame in order to define the axis. Then I'll enter my reference center and z direction to define the axis of revolution. Enter -180 degrees for the angle of revolution, and click OK to save this surface and exit the Revolve panel. To create my far-field domain, I'll click over to the Details panel to set my average grid spacing to something more appropriate for the far field, and create the far-field domain similarly to how the surface mesh for the wing was initially created. I'll create the symmetry domain by going to Create, Assemble Special, Domain, where I can define both the outer and interior edges that define the symmetry domain. You want to ensure that the interior edge is oriented in a direction opposite the outer edge, and then click OK to save the domain and exit the Assemble Domains panel. With all of the domains created thus far selected, I can create a block by clicking the Assemble Blocks toolbar shortcut. The Messages window confirms that a new block was created and the block appears in the List panel. 3D T-Rex will be used to extrude layers of anisotropic tetrahedra from the wing surface and then fill the remaining interior volume with isotets. T-Rex will stop advancing layers from the wing surface once cells have reached isotropy, or a user-specified mesh quality parameter would be violated with creation of new tetrahedra. This allows a smooth transition of cell volumes from the anisotropic tetrahedral layers to the isotets in the interior volume mesh. It is also why having a uniform surface mesh where the area ratio of surface cells are below a threshold value of 4. First, select the block via either the List panel or display window. Select T-Rex from the Grid menu and click over to the Boundary Conditions tab. Again, I need to set up boundary conditions for the wing and symmetry plane. The wing boundary condition is set to a wall-type boundary condition, and this time the initial spacing is going to be the initial Y+ spacing required for your simulation. Fun3D's Adjoint solver doesn't support wall functions, so I set the initial spacing that results from the flow Reynolds number, free stream temperature, characteristic length, maximum length of the model in which I expect to have a boundary layer, and Y+ of 1. For this case, and these flow conditions, the Y+1 spacing is 6.5 e to the -5 inches. Next, I need to assign the wing surface mesh and symmetry domains to their corresponding boundary conditions by selecting them in the display window and clicking the Set checkbox next to the appropriate boundary condition name. Back on the T-Rex tab, I can specify a maximum number of layers of anisotropic tetrahedra for T-Rex to extrude. Since T-Rex's extrusion will stop automatically when cells reach isotropy, the parameter can be set to an arbitrarily large value. Here, I'll set it to 100 as an example. With a finite trailing edge, I want to direct T-Rex to use a single normal at each of the two convex corners of the trailing edge rather than use multiple normals as would be necessary for a sharp trailing edge. Somewhat unintuitively, the full layers parameter controls this. To use a single normal, I set this parameter to 1. I also want to change the growth rate parameter from its default value to something more appropriate like 1.2, as well as enable the Push Attributes option. Enabling the Push Attributes option automatically propagates the block T-Rex attributes to domains set with a boundary condition type of match. Specifically, the initial spacing, the number of layers, and the distribution of points on the interior of the T-Rex block will automatically be matched on these domains. In this example, this refers to the symmetry domain. I also want to prevent anisotropic tetrahedral cells from being created if doing so will result in one of their angles being larger than 165 degrees. I can apply this constraint by expanding the skew criteria frame, unchecking the Use Defaults option, and entering 165 into the max angle entry field. Over on the Attributes tab within the algorithm frame, I'll turn up the boundary decay factor again from 0.5 to 0.85. Finally, I can click over to the Solve tab and click Initialize to begin generating the volume grid. As the volume grid is being generated, I can watch how many full layers of anisotropic tetrahedra are created. In this case, 36. I can also monitor in the display window to see where the grid extrusion has stopped early. This is indicated by red dots in the display window. In this case, as expected, the layers initially stop advancing near the wing tip at the trailing edge since the initial cell size of those cells was a bit smaller than the rest of the surface mesh. As a result, the extrusion finished sooner in this localized region. Directly from within the Solve panel, the volume mesh quality can be examined. I'll select Max Included Angle from the pull-down menu and click over to the Examine panel. The max included angle of all cells is about 165 degrees. We can also visually inspect the mesh while creating some cuts. I'll save the grid and exit the Solve panel by clicking OK. The last few steps involve setting the CAE solver to Fun3D, creating Fun3D specific boundary conditions, and then exporting the mesh. From the CAE menu, choose the Select Solver option, select NASA Fun3D, and click OK. The currently selected CAE solver and the solver dimension are shown at the lower left of the pointwise window near the progress bars. Creating and applying boundary conditions in the SetBC panel proceeds almost exactly the same as setting boundary conditions for T-Rex. Create a new boundary condition, select the appropriate boundary condition type, select the corresponding domains in the display window, and set them to that boundary condition by clicking the Set checkbox. Note that the boundary condition types are CAE solver specific, and only the supported boundary condition types for the currently selected solver appear in the CAE type pull-down menu. Finally, you can export the mesh using the CAE solver-specific grid file format by selecting the block from either the list panel or display window, and then from the File menu, choosing the Export CAE option. An Open Save dialog window appears where you can name and browse to the location where you want to save the grid files. Once you specify a file base name and click Save, the Export CAE panel opens where you have the option to combine all of the anisotropic tetrahedra into prisms. Using this option was what allowed us to investigate the influence of near-wall cell types on accuracy and convergence of solutions in the adjoint-based mesh adaptation procedure. I'll enable this option in this example to demonstrate this feature. Once cell combination completes, a table is printed to the Messages window and shows that cell combination reduced the number of cells in our mesh from about 1.5 million T-Rex cells to 889,000, which is especially beneficial for users of cell-centered solvers. Now that I have exported my mesh, I'm ready to set up and run Fun3D. Both the grid and the boundary condition files have been exported from Pointwise. A solver input nameless file is also required to define parameters that govern initial flow conditions, solver settings, frequency of solver output, as well as mesh adaptation specific parameters, which I'll cover in a bit more detail shortly. The built-in Refine1 mesh adaptation library allows you to specify boundaries where the cells are to remain fixed. It also allows you to specify analytical surface definitions for planar boundaries in which points are allowed to move. In cases in which the boundary is not planar, the far-field boundary, in our example, points on the boundary need to be fixed. This is done via a text file that uses the project base name with a .freeze extension. For boundaries that are planar, such as is the case with the symmetry plane in our example, a file named flow_input provides a way to indicate that all of the points that lie along a y = 0 plane can be adapted. The adjoint solver has a specific input file named rubber.data for defining the adjoint cost function, and this file is easily generated using a Ruby script named F3D that is included with the Fun3D distribution. In this example, the lift-to-drag ratio was specified as the engineering output to be used in error estimation. The F3D script also allows automating the mesh adaptation process, from setting up the directory structure, maintaining an up-to-date set of run files for each adaptation cycle, running the flow and adjoint solvers, calculating the error estimate for the objective function, and then adapting the mesh accordingly. Thus, the F3D script itself uses an input file named case-specifics to provide some level of control over automating the process. Most all of this information is covered in detail within the user manual, so I won't delve into too many specifics. I will highlight some of the parameters governing mesh adaptation in the Fun3D namelist input file, however. Within the adapt mechanics namelist, the adaptation library to be used and the number of adaptation cycles can be specified. There is also a parameter named AdaptFreezeBL, which prevents modification of the grid within the specified distance of solid wall boundaries. It is used to preserve an existing boundary layer grid structure and is specified in grid units. A distance that equates to a y plus of approximately 100 is specified here. In the adapt metric construction namelist, the adapt error estimation parameter defines the method used for providing an estimate of error in the engineering output. Typically, you should opt for the default embed method here, but I selected the single method instead due to limitations on available computational resources. I only had 32 gigabytes of memory available, and the single method uses far less memory than the embed method, but does not provide as good an estimate of the error. The adapt complexity allows users to control how many points can be inserted into the mesh during mesh adaptation. This helps limit the total number of points in the grid in order to ensure that the mesh does not exceed the computational resources available. The parameters available in the case-specifics file allow you to change this value and thereby gradually increase the size of the adaptive grid at each adaptation cycle. This is probably a good time to mention that Fun3D's Refine 1 mesh adaptation library ignores prisms altogether and will only adapt tetrahedral cells. You may also recall that in the adapt mechanics namelist of the Fun3D input file was a parameter named AdaptFreezeBL, which prevented modification of cells within a specified distance of solid wall boundaries. For the tetrahedric grid case, this was set to preserve the existing boundary layer grid structure up to about the middle of the log layer. However, in the case of the mixed prism tetrahedral grid, the near wall mesh was ignored entirely by Fun3D's mesh adaptation library. In our prism mesh example, all of the cells approximately 3.5 inches normal from the solid wall boundary were not modified. After both cases had run through 10 adaptation cycles, I sorted through some of the results to evaluate each approach. This first plot shows pressure coefficient plotted for a few different sections along the wing span. Each case is compared to available empirical data as well as another solution that was run using an overly refined mesh. Qualitatively, the mixed prism tetrahedral case appears to match the experimental data slightly better than the all-tetrahedral grid, particularly in the vicinity of shocks along the upper wing surface. However, neither case matches as well as the solution from the overly refined mesh case. While grid adaptation is formulated to reduce discretization error, it has no effect on modeling error. Being able to match empirical data is often an exercise in controlling both. Next, I plotted a comparison of grid convergence. Here, the lift-to-drag ratio is plotted for each adaptation cycle where the mesh is being successively refined. N represents the number of grid points in the mesh. The prism tetrahedral case doesn't show too much of a change in the engineering output over 10 adaptation cycles, whereas the tetrahedral case looks as though it may need a few more adaptation cycles before converging to a value. I think the takeaway from this and the previous chart show that in order to leverage the maximum potential of mesh adaptation, modification of the grid near solid wall boundaries is especially important. You can accomplish this in one of two ways by either using an all-tetrahedral mesh and setting the adapt-freeze BL parameter within the Fun3D nameless input file, or use T-Rex in pointwise to extrude layers of tetrahedra to be combined into prisms at a distance equivalent to the middle of the log layer instead of extruding to an isotropy condition. To this recommendation, I would also add that for best results, one might consider increasing the surface resolution of the initial mesh since the grid points there are frozen, and then utilize a coarse and viscid grid outside of the boundary layer grid since it will be refined. We've reached the end of this webcast, and I want to thank you for being with us today. If you have any questions about this webcast, then please don't hesitate to post your questions to the YouTube comments section below or send your questions to us at letstalk@pointwise.com. You can also tweet your questions to Pointwise using the Let's Talk Meshing hashtag.